this video, you're going to be introduced to something called the geometric mean and taught how you can use it to solve problems involving altitudes in right triangles. Now, first of all, we have to talk about this new word, mean proportional. First of all, mean proportional means the same thing as geometric mean, and it's really a fairly simple concept that sounds more difficult than it is. It just says that when you have a proportion where the two means are equal to each other, then we can call that mean the mean proportional or the geometric mean between the other two numbers. So if you take a look at the proportion that's given to you there on the paper, 2:8, is 8:32, notice that 8, the number in the means position, is exactly the same. What that means is that 8 is the mean proportional, or in other words, the geometric mean between the other two numbers, which in this case are 8 and 32. Sorry, 2 and 32. So in example 1, if they want us to find the mean proportional between 8 and 12, we're going to go ahead and set up a proportion where our means numbers are exactly the same. And since that mean proportional is what we're looking for, I'm going to go ahead and call that x. The two numbers that it's the mean proportional for are 8 and 12, and I'm going to put those in the other two positions in my proportion. So now when I go ahead to cross multiply in order to solve, I find that x squared is equal to 96. And when I take the square root of both sides, I find that x can either be the positive or the negative square root of 96. When we talk geometric mean or mean proportional, we always talk the positive value of x. So I'm going to go ahead and reject that negative root. But at the same time, I'm going to remember that anytime I have a number under the radical sign, I have to make sure that that radical is in simplest radical form. So while 96 isn't a perfect square, 16 will go in there exactly 6 times, making that mean proportional, or that geometric mean, however you want to say it, equal to 4√6. Now you might be saying to yourself, what does this have to do with geometry? Well, that's where we're going to go with this next. When you draw the altitude to the hypotenuse in a right triangle, some really, really cool things happen. In that we end up with two triangles that are similar to both the original triangle and to each other. And this allows us to create some different types of proportions that we can use to then solve some problems regarding the triangles. So that's what makes this so neat. Now on my copy, the right angle at B didn't print, so I'm going to go ahead and draw that right angle in at B. And because segment BD is the altitude that's being drawn to hypotenuse AC, I know by my definition of altitude that it's always going to form right angles with the opposite side. So I know that those angles at D have to be right angles. So I'm going to go ahead and draw that in there as well. I want to talk a little bit about the pieces or the parts or the anatomy of this big right triangle. In triangle ABC, segment AC is going to represent the hypotenuse because it's opposite the right angle B. So I'm going to label that with a capital H for hypotenuse. Notice that segment BD, the altitude, splits the hypotenuse into two equal parts. And for lack of a better word, I'm going to call them part 1 and part 2. And I'm going to label them with a P1 and P2. We said that segment BD was the altitude of that triangle, so I'm going to label that with a capital A for altitude. And then segments AB and BC represent the legs of that original big right triangle. So I'm going to label them leg 1. And notice that leg 1 is in the same little triangle as part 1. That's important. And leg 2, and pay attention to the fact that leg 2 is in the same little right triangle as part 2. That's important. What I'm going to do at this point is I'm going to pay some attention to these little right triangles, these smaller right triangles that are formed when we draw that hypotenuse. So I just made one of them red and one of them purple. And what I'm going to do is I'm going to rotate those around so that they have the same orientation as triangle ABC, our original big triangle. So I'm going to go ahead, clear some space over here so I can go ahead and lay those guys down with their altitude pointed, or sorry, their hypotenuse in the same place as the hypotenuse was for that big right triangle. So I'm going to put their right angles up at the top. And if I look at the little red right triangle first, his right angle's at D, so this point up here has got to be D. and his hypotenuse is AB. And I'm now going to label this little triangle with all the same notation as I used over here in the big triangle. So AB we called L1, BD we labeled with an A, and AD we labeled with a part 1. And then I'm going to do exactly the same for my little purple triangle. In my little purple triangle, D is the right angle, so here's D, and BC is the hypotenuse, so BC lays down here. DB we labeled with an A for altitude in the big triangle, so I'm going to bring that over to our new smaller triangle. BC in the purple triangle we labeled with a leg 2, so I'm going to bring that over here, label in my smaller triangle. And DC, the third side, we labeled with a part 2, so I'm going to bring that over here. Now these little triangles, the red one and the purple one, are similar both to each other and to the larger original right triangle. But what I'm going to do now is I'm going to use these two smaller triangles in order to set up some proportions. The first proportion that you're going to need to be aware of says that the length of the altitude to the hypotenuse in a right triangle is going to be the geometric mean between the parts of the two segments of the hypotenuse. Well, here's where that proportion came from. We're comparing part 1 in one triangle to the altitude in the second, and we're saying that ratio is going to be equal to the altitude in the first triangle compared to part 2 in the second. And notice, again, this guy is the geometric mean because that number in the means position, in this case the altitude, is exactly the same in each ratio. Now, I'm going to give you the little mnemonic to remember this. I'm going to call this guy PAAP. So PAAP, again, just says that the altitude drawn to the hypotenuse in a right triangle is always the geometric mean between the two parts of that hypotenuse. And I would probably change that word lengths to make that parts. So that's the first proportion that you need to be aware of. The second proportion says that the length of each leg in that right triangle is going to be the geometric mean between the length of the hypotenuse and the length of the segment that is adjacent to that hypotenuse. This sounds a little bit more difficult than it really is. What they're saying here is they're saying if we compare the length of the hypotenuse in the original triangle to the first leg, which we can do because they're corresponding parts of similar triangles, so hypotenuse compared to L1 is going to be equal to the ratio if we compare L1 to the first part. So again, pay close attention to the fact that the leg is the geometric mean. He's exactly the same in both proportions. Now some of you might be saying, but Ms. McKeon, what if we wanted to compare the length of this hypotenuse to the second triangle? Well, you can do that too. So if we compare the length of the hypotenuse to leg 2, that's going to be equal to what we get when we compare leg 2 to part 2. And again, notice that the leg, in this case the second leg in that big right triangle, is the geometric mean between the hypotenuse and its adjacent part. Now this sounds really, really, really confusing. In fact, it is kind of confusing. But the more practice you get with these, the better they're going to become and the easier they're going to become. That said, I have some words of wisdom for you as we move into the practice problems. My first piece of advice would be to label all of the pieces and all of the triangles every time. Label your hypotenuses, label your parts, label your altitudes, label your legs. All right, so I'm going to go ahead and head into these problems thinking to myself in the back of my head that I want to label every part of every triangle every time. So I'm going to go ahead and take a look at example 2, and the very first thing I'm going to do is start by labeling the pieces. So the hypotenuse is that segment right there, which means the two parts, part 1 and part 2, however you want to think about them, are there and there. Leg 1, leg 2, my altitude here in this particular case is 10. Since I find it helpful, I'm going to take my highlighter and highlight that altitude. And I can see very clearly that in this question, I'm dealing with the altitude. I know the altitude is 10. This is a question that involves and utilizes the altitude. And anytime I have a question that involves or utilizes the altitude, the proportion that I want to use is the PAAP proportion. So I'm going to go ahead and get that down on my paper. I want to do part 1 over the altitude equals the altitude over part 2. And then I'm just going to substitute the pieces that I marked in my picture into my proportion. So my part 1 was x. My altitude is 10. My altitude is 10. And my part 2 is x plus 21. Notice that in my proportion, the means are identical. If these means aren't identical, that means I made a mistake when I set up my proportion, and I had better go back and revisit that proportion because it's wrong. So as you know from your algebra class and you're working here this year, the easiest way to solve a proportion is going to be to cross multiply. So I'm going to go ahead and cross multiply going in one direction, x times the quantity x plus 21 equals 10 times 10. Or in other words, when I distribute the left side of this, x squared plus 21, x is equal to 100. I see that due to the fact that I have an x squared in this problem, that it's a quadratic equation. And in order to solve a quadratic equation, you've got tons of strategies. You can solve by factoring the quadratic formula. You can put it in your calculator and find the zeros. You can do completing the square. I'm going to see or try factoring and see if factoring will enable me to solve this quadratic equation. So I'm going to go ahead and subtract the 100 from both sides. And then when I attempt to factor, I find this will factor into x plus 25 times x minus 4. Keep that equation set equal to 0. So what this means is that my first factor, x plus 25, must be 0. Or my second factor, which is x minus 4, has to be equal to 0. So either the value of x is negative 25, or the value of x is equal to 4. If I think about what x represents in this particular problem, x represents the length of a line segment. X represents the length of part of the hypotenuse. Since x represents a length, and I know that length can't be negative, I know therefore that my negative solution is inappropriate and must therefore be rejected. So the value of x in this particular problem is 4. Okay, in looking at example 3 then, and keeping in mind the helpful hints that I gave you, you want to make sure you label every part of every triangle every time. That is key. That is huge. So in this particular problem, my hypotenuse is the piece marked with a length of 12. The two parts of the hypotenuse, one of which I know and the other of which is called x. The two legs of my triangle, one of which I know is 6, the other of which I don't know, and the altitude. And again, I'm going to grab my highlighter and I'm going to highlight the altitude. So if I look at this particular problem, the first thing that I'm going to do is to try PAAP. But in this case, I don't know the altitude. I don't want to know the altitude. This problem doesn't have anything to do with the altitude, and therefore the PAAP proportion is not going to be helpful. And since PAAP is not going to be helpful, I'm going to use instead the HELP proportion. So the hypotenuse in this question is 12. The leg is 6. Leg is 6. And in this particular case, the last part that I want to fill in there can be a little tricky. I have in the picture two parts. I want to use the part that's in the same triangle as my leg is. So my leg of 6 is in the same triangle as my part of x. And that right there tells me that the part I'm going to use in my proportion is the part with length x. Again, the easiest way to solve a proportion is to cross multiply. So 12 x's are equal to 36. And the value of each x then is equal to 3. Now I've given you a lot to think about in this video. As always, I want you to think about what are the most important ideas, what are the things that you're going to need to remember and take away from this video with you, and then see if you can apply what you've learned to solve the questions on the next page.